Hey, so let me guess. You've got a massive statistics exam tomorrow, your textbook suddenly looks like it's written in ancient Greek, and that familiar panic, yeah, it's starting to set in. But look, take a deep breath. You're in the right place. Welcome to a high-yield, purely focused explainer designed to cram Charles Wheelan's brilliant book, Naked Statistics, straight into your brain. We're going to decode the jargon, focus on exactly what you need to know, and help you absolutely ace that test.
Okay, so here's our roadmap for this explainer. We're going to break this down into 5 buckets: describing the data, probability and expected value, the magic of inference, finding hidden relationships, and finally, avoiding common stat traps.
All right, let's jump right into part 1, describing the data. We're talking mean, median, and standard deviation.
So when you take a giant pile of real-world data and try to summarize it, you might actually see a question exactly like this on your exam. What is the best measure of middle-class economic health? Now, your gut instinct might be to just say, oh, look at the average income. I mean, it sounds right, doesn't it? But is a simple average always the right answer? Let's think about why that might actually be a trick question designed to test how well you understand data distribution.
Picture this. You've got 10 average people sitting on bar stools in a local pub. If we calculate their mean, or average income, let's say it's about $50,000. Not bad. But now, imagine Bill Gates walks into the bar and sits down. Suddenly, the mean income of everyone in that room shoots up to several billion dollars. Does that mean the original 10 people are magically billionaires? Obviously not. The mean is getting massively skewed by an extreme outlier. The median, on the other hand, that's the exact middle point. If you line everyone up by income, the median is just the person standing right in the dead center. Even with Bill Gates in the room, that median stays totally stable. So remember this for your test. If the data has extreme outliers, like a nation's wealth, the median is almost always your safest, most accurate answer.
Okay, moving on to standard deviation. Just think of a dartboard. If you're a pro, your darts are all tightly clustered right near the bullseye. That represents a small standard deviation. But if you're a beginner, your darts are probably scattered all over the board. That's a large standard deviation. Basically, it tells you exactly how spread out your data points are around the average. Understanding this is absolutely vital for adding context, especially when you're looking at a normal distribution, a bell curve, to interpret risks and outcomes.
Which brings us to part 2, probability and expected value. We're going to look at risk, binomials, and Schlitz beer.
See, predicting uncertainty isn't just about rolling dice. Consider how the Schlitz Beer Company used basic probability for this brilliantly sneaky Super Bowl marketing campaign back in 1981. They did a live blind taste test on TV, but here is the genius trick. They didn't just pick a random sample of people. Nope, they explicitly only selected loyal drinkers of their rival, Michelob. Why would they do that? Because Schlitz knew that in a blind test, similar mass-market beers are statistically almost impossible to tell apart. It's essentially a binomial experiment, just a fancy way of saying a coin flip with a 50-50 outcome. By only testing Michelob fans, Schlitz guaranteed that roughly half of a rival's loyal customers would blindly choose Schlitz on live TV. It looked like this massive upset win for the brand, but really, it was just basic probability doing the heavy lifting.
Now, to make those kinds of smart bets yourself, you really need to understand expected value. Think of this as your mental checklist for the exam tomorrow. Step 1. Identify all possible outcomes of an event. Step 2. Weigh those outcomes by their specific probability of actually happening. And Step 3. Assess the payoff to guide your final decision. Honestly, this is exactly how big businesses evaluate major investments, and it's how football coaches mathematically decide whether to go for a 2-point conversion.
Let's apply that checklist to a really relatable everyday scenario. Should you buy the extended warranty on your brand new $99 printer? Statistically speaking, no. When you weigh the relatively low probability of that printer actually breaking against the surprisingly high upfront cost of the warranty, the math just doesn't favor you. The insurance company has already calculated the expected value, and you better believe they priced that warranty so that they make money on average, not you. It's a bad bet. Just keep your cash.
All right, on to part 3, the magic of inference. We'll cover the central limit theorem, polling, and sampling. So inference is basically the art of making powerful, sweeping deductions about massive populations using just a small, cleverly chosen slice of data. But before we infer anything at all, we have to talk about data quality. Wheelan uses a fantastic analogy here. Compare the data to an American football team's offensive line and the statistician to the star quarterback. Look,
If the offensive line is terrible and just can't block, the star quarterback is going to get sacked every single time, no matter how insanely talented they are. It is the golden rule of statistics: garbage in, garbage out. If your data, meaning your sample, is flawed or biased, your incredibly complex statistical analysis will fail entirely.
But if your data is solid, you unlock the absolute MVP of the statistical world, the central limit theorem. Wheelan literally calls this the LeBron James of statistics. You absolutely must know this for your test. It states that if you take properly drawn samples from a population, the sample means will form a normal distribution, yep, that familiar bell curve, around the actual population mean. And the craziest part? This happens regardless of what the underlying population's shape looks like. It is the core engine that makes literally all modern polling and inference possible.
Let's see that in action. When a poll tells us that 64% of Americans support the death penalty, they obviously didn't go out and ask all 300 million people. They asked a representative sample. And thanks to the central limit theorem, we can calculate what's called a standard error and a confidence interval. Generally, the larger your sample size, the smaller that standard error gets, and the more confident we can be in predicting the true sentiment of the population. But always remember, the poll is only as good as its neutral question wording and its unbiased sampling.
Moving right along to part 4, finding hidden relationships, correlation versus regression.
I can pretty much guarantee your exam is going to test you on how two completely different variables interact with each other. So here is exactly how to keep them straight in your head. Compare Netflix recommendations with medical health research. Netflix uses correlation. They don't actually care why you like a movie. They just observe the pattern that people who rate The Matrix highly also tend to really like Inception, and they match your tastes. But medical studies, they use regression analysis. If researchers want to know if job stress actually causes heart disease, they can't just look at a simple correlation. They have to use regression to isolate the specific effect of job stress while mathematically controlling for other variables like smoking, age, and education. To put it simply, correlation observes patterns, regression isolates specific variables.
For correlation, make sure you memorize these bounds for the correlation coefficient. It always ranges from -1 to +1. A coefficient of 1 is a perfect positive relationship, meaning as one goes up, the other goes identically up. -1 is a perfect inverse relationship. And 0, that just means there's absolutely no correlation at all. Lock those numbers in your brain for tomorrow for sure.
This ability to isolate variables is exactly why Wheelan calls regression analysis the miracle elixir that supersizes the scientific method. It's just incredibly powerful. By isolating variables, we can untangle immensely complex social issues. For example, we can use regression to figure out the actual impact of daycare on a child's school performance by stripping away confounding factors, like family income or the parent's education level. It's essentially statistical detective work at its absolute finest.
All right, final stretch, part 5, avoiding common stat traps. We're talking biases, causality, and missing variables.
Okay, let's put a giant, flashing warning label on this section because this is exactly where professors absolutely love to hide trick questions. Okay, rapid fire time. Here are the common data biases you need to memorize. Selection bias. That's when your sample just doesn't represent the broader population. Self-selection bias, meaning volunteers for a study are fundamentally different from non-volunteers. Publication bias. Boring or negative results almost never get published in journals. Recall bias. Human memory is terribly flawed. Survivorship bias. This is when you only analyze the successful outcomes, like evaluating mutual fund performance but conveniently ignoring all the funds that went bankrupt. And finally, healthy user bias. People who take vitamins also tend to exercise and eat well, which totally muddies the waters. Seriously, know these biases inside and out.
Next up, we've got common regression mistakes. First off, don't try to analyze nonlinear relationships with linear tools. It won't work. Second, watch out for reverse causality. Did A cause B, or did B actually cause A? And the really big one, omitted variable bias. Let's say a study shows that playing golf correlates with a much higher risk of heart attacks. Does golf literally ruin your health? No way. The study omitted the variable of age. Older people are more likely to play golf, and older people are inherently more likely to have heart attacks. If you leave out a crucial variable like that, your whole analysis is completely useless. Which leads us to the ultimate, absolute test-saving rule. Say it with me. Correlation does not equal causation. Just because two things happen together does not mean one caused the other. Like, data shows that SAT scores correlate heavily with the number of televisions in a student's house. Do TVs magically make you smarter? No! Having more TVs usually just indicates a higher family income, which heavily correlates with better access to education and tutoring. Never, ever fall for the causation trap on your exam.
So as we wrap up this explainer, I want to leave you with this thought. If statistics rarely unveil absolute, undeniable truths, how will you use these tools to build a circumstantial case out of imperfect data? Because honestly, that's the real test. Statistics isn't just about crunching a bunch of numbers. It's about sharpening your judgment, spotting bad math in the real world, and making much better decisions in a highly uncertain world. But hey, you have the tools now. So get a good night's sleep, put your trust in the central limit theorem, and go absolutely ace that exam tomorrow. Thanks for hanging out and learning with me.